Okay, so for our second talk on day 3, we're very happy to have Silviu Pufu from Princeton University. Silviu has made many contributions in holography and supersymmetric and superconformal field theories and questions about RG flows and monotonicity. So please, Silviu, take it away.
Okay, so just to confirm, you can hear me, you can see the slides?
Yeah.
Okay, good. So thanks a lot for the opportunity to speak. So I wanted to talk about some work that I did with Damon Binder, Dan Friedman, and Bernardo Zahn. You can also see my pointer, right?
Yes.
Yeah, very good. And I'll also mention some work in progress with Dan Friedman and Bernardo at the end of the talk if there's time. And I have to apologize for not talking about defects in CFTs or CFTs with boundaries. The only boundaries that will appear in this talk is the fact that there would be, from the ADS CFT correspondence, there would be a CFT on the boundary of a space in which there's gravity. So let me start a talk by saying that the sphere free energy in three-dimensional conformal field theories and superconformal field theories has played various important roles, and let me describe some of them. So the first one of the most important ones is that the sphere free energy provides a measure of the number of degrees of freedom in three-dimensional conformal field theories. It obeys the so-called F theorem. Another one is that's sort of related in some way, that in theories with n equal to supersymmetry and some abelian flavor symmetry. So suppose that such a theory arises at the infrared fixed point of some RG flow that preserves some abelian flavor symmetry. And then the infrared fixed point, the conformal symmetry is emergent, but the superconformal algebra, the n equal to superconformal algebra, also contains some R symmetry. So the question is, what is the R symmetry at that infrared fixed point? It could be any linear combination of the R symmetry in the UV and the flavor symmetries, and that's a sphere free energy plays a role in answering that question through the F extremization or F maximization procedure. Another thing about the sphere free energy is that it can be computed exactly using supersymmetric localization, and not just for a CFT. So if it's a conformal field theory, you can place it on a round 3 sphere. Because the sphere is conformally flat, but one can also deform the sphere using various parameters. For instance, one can squash the sphere, or one can introduce mass parameters. And even with these deformations, it can be computed exactly using supersymmetric localizations. And this has been used to test dualities and for other purposes. And one of those purposes is this, and this is something that we've been doing for the last few years, that one can take the sphere free energy as a function of parameters and then take derivatives with respect to the parameters and then evaluate the derivatives at the conformal point. So for instance, for 0 mass, and when the squashing parameter corresponds to the round sphere. And what that does is that gives some correlation functions. So these parameters couple to some operators that are integrated over the sphere. So if we take derivatives, we get correlation functions of those integrated operators. And this can be used in numerical and in analytical bootstrap studies. And just so the last 2 points are also true in 4 dimensions. And I don't know if Pedro is still here, but in the case that he was talking about, the n equal 4 super Mills with the Wilson loop, there are additional constraints from supersymmetric localization that are just integrated correlators that can be obtained by taking derivatives with respect to the masses. I can discuss that more in the discussion session. So let me elaborate a little more on the last 2 points, and then tell you well, raise some questions about this. So let's assume that we're looking at the 3D superconformal field theory with some flavor symmetry. There's some flavor symmetry. There's a conserved current, J mu, dimension 2 and spin 1, and that sits in a, yes.
Yeah, I'm sorry, just it's about the previous slide. Can I ask a question?
Sure, yeah, of course.
This might be stupid, but how does it work in 4D? So isn't there some anomalies or log divergence in this quantity? So why can you get correlators at separated points as well?
Yeah, if you take enough, sure, if you take enough derivatives with respect to B and M, then those go away.
I see. Okay. So but the finite part is not ambiguous, because if the anomaly has a log, then you would say the finite part has an ambiguity.
Right. So one has to be careful about what derivatives exactly you take, and you have to take the derivatives that are not ambiguous. Some of them would be ambiguous, some of them wouldn't. So you just have to take the ones that aren't.
I see. Thank you.
Okay, good. So if there's some flavor symmetry, so this is 3D, I'll talk about 3D and this talk, but of course, it would be interesting to do the same thing in 4D. There's a flavor symmetry, there's a conserved current, and the current sits in a superconformal multiplet with other operators. These are conformal primaries, and in particular, there's 2 scalar operators, one of them of dimension 1 and the other one of dimension 2. The one of dimension 1, I call it J, the one of dimension 2, I call it K. And then if I normalize these operators in a certain way, and I normalize them based on just give you what the 2-point functions are, and there's some normalization constant here, tau, it's not going to play a role. Then if we take the conformal theory, we put it on a round 3 sphere, and then we can deform it in a way where we preserve using operators of this from this multiplet, namely J and K, in a way that preserves n equal 2 supersymmetry on the 3 sphere. N equal 2 supersymmetry without conformal symmetry, just n equal 2 supersymmetry on the sphere means SU2/1 times SU2 as a super algebra. And the deformation is just some parameter M, and then I over the radius of the sphere times J plus K. K has dimension 2. This combination also has dimension 2, and M, the mass parameter, has dimension 1. So this is the construction of the real mass deformation of the theories. These are the mass parameters, the sphere free energy depends on. And yeah, in this talk, I will not consider squash spheres, but I will consider spheres, theories on a sphere deformed by these mass parameters. In general, if we have a Lagrangian theory, that would be a term of order m squared, but I'll make a comment about that in the next slide, and then we don't have to think about that anymore. Okay. So a few comments about this construction is that the coefficients of these scalar operators J and K that are proportional to the real mass parameter M are background values for scalars in a vector multiplet that couples to the conserved current multiplet. So we can take this conserved current multiplet, we can couple it in a superconformal way to a vector multiplet, the gauge field, and also has a couple scalars, and then set the gauge field to 0, give the scalars expectation values that are proportional to M in a way that preserves supersymmetry. And then one also obtains this expression. The other comment that I wanted to make is that the order m squared terms in theories with Lagrangian descriptions is there because it's required by supersymmetry, and it can be interpreted as a contact term in the OPE of these operators K. So we can either write it down and not consider such a contact term, or we don't write it down and we consider a contact term. So I want to take the second point of view, so then I just don't have to worry about it. But of course, then in computations, one has to worry about this contact term. And another comment that I wanted to make is that if one continues this parameter M to pure imaginary values, these are precisely, this would give the lead to the trial R charges that are used in the F maximization procedure. So that's the connection to that, but I will not use this fact or say more about it. But this perspective shows that if we then take derivatives with respect to this parameter m of the log of the partition function, then we get correlation functions of these operators ij plus k integrated over the sphere. So these are integrated correlators. And I said this before, that I should emphasize it again, that the left-hand side can be computed from supersymmetric localization in specific models. So this would be, so in practice, we know the left-hand side. So this is just some information that we learn about this correlation function. So why is this useful? Well, I can just tell you one application in this slide. I won't elaborate on it because this is another talk. So, for example, so suppose that we're interested in studying ABJM theory at transimultaneous levels k equals 1 or 2, where there's n equal 8 supersymmetry. This theory has some scalar operator called S. By the way, I mean, we could do this in 4D where we'd be interested, say, in n equal 4 superangles, but let's just talk about ABJM theory. There's some scalar operator S of dimension 1 that transforms in the 35-dimensional representation of the SO8 R symmetry algebra. So this is in an n equal 8 theory, but from an n equal 2 point of view, some of these components of S, some of the 35 S's, namely 3 of them, could play the role of the operators J that also had dimension 1 that I mentioned here. Now, independently of what I said before, using conformal symmetry and supersymmetry and analytic properties of Witten diagrams in Mellon space and crossing symmetry and Lorentzian inversion formula, one can actually find an ansatz for the correlation function, for the 4-point function of this operator S at strong coupling. So in the 1 over n expansion. So here I wrote down the 1 over n expansion. I wrote it in terms of CT, which is goes like n to the 3/2. CT is the coefficient and the stress tensor 2-point function. And using all these facts, one can actually figure out what all these functions are. These are the explicit functions of position, but one just doesn't know what the coefficients that appear here, the coefficients that are in red. One doesn't know what they are. So then, what is the role of the these integrated correlators that we can compute in this case using supersymmetric localization? Well, the role is that using them, we can plug this ansatz into that integrated correlator. Well, from the S's, we can figure out the correlation functions of the J's, and using supersymmetry, we can figure out the correlation functions of J's and K's, and then compute that integrated correlator, and then find constraints on these coefficients. And in some cases, for example, if there's just one coefficient as a certain order in 1 over CT, then one can determine that contribution exactly. So using integrated correlators, one can determine some of these constants. And we've done this with 2 such integrated correlators. So that means that up to this order, up to 1 over CT to the 19/9, one can actually determine, using just these principles and supersymmetric localization, one can determine the correlation function. And I find this kind of remarkable because, so the indices here correspond to the kinds of Witten diagrams that contribute to these functions. So for example, this one, the second one here, would be correspond to contact interactions where the interaction vertices come from a supersymmetrization of Riemann to the 4th interaction in M theory. And that full interaction in the Lagrangian, the interaction term for that is not completely known. So it's kind of remarkable that using just general consistency conditions, as well as the result from supersymmetric localization, one can find one can find the answer to those Witten diagram computations, even though we don't know exactly what the interaction vertices are. So that's kind of motivation. So then, you might wonder, so what is the sphere free energy actually, and its derivatives? What is that computing? You can ask this question either in the CFT. So for example, what is it computing in terms of CFT data? Or you can ask it in holography. So, in terms of the CFT data, maybe it's computing some OPE coefficients or something, or maybe something more complicated. And in holography, well, maybe it's computing some sort of couplings, or maybe it can compute all the bulk couplings. So in particular, can one determine all the constants that are in SSSS? Suppose we go to high order in 1 over CT, can one determine all the constants using integrated correlators? If there are also examples, not just ABGM theory, there's many examples of superconformal field theories with holographic duals with just n=2 supersymmetry. And those have unprotected single trace operators, some scaling dimensions usually involve square roots. Can one extract from the sphere free energy using this kind of approach? Can one extract the scaling dimensions of these unprotected single trace operators? Or as an alternative, is there a protected set of OB coefficients that is captured by the sphere free energy as a function of the mass? And thinking about taking derivatives and evaluating the mass equal to 0. So maybe as a little bit of a spoiler, I can say that the answer to all these 3 questions here is no. And a possible hint, don't know really what to make of this, may not know what to make of this at this point in the talk, that in some examples, it was noticed, for instance, in ABGM theory, it was noticed that the sphere free energy as a function of m is proportional to the prepotential of the supergravity theory, the 2 derivative levels in the bulk. Well, the prepotential is like some sort of special interaction, so that sort of suggests that maybe there are some special interactions in the bulk and the sphere free energy is capturing. Good. So please interrupt if there are any questions. So let me try to address this question: what is the sphere free energy computing in holography? So by the sphere free energy, I mean as a function of f as a function of the mass, of the real mass parameters. So to address what it's computing in holography, let's just think about holography. So we have ADS4, and we have some effective action around ADS4 that depends on what field theory we're considering. But this action must be supersymmetric, so it must be invariant under the supersymmetry algebra of ADS4, n=2 supersymmetry algebra, which is OSP24. And as I said before, if we take derivatives with respect to the mass of the log of the partition function, we get some integrated correlator of this operator ij plus k. But from the point of view of the bulk, this can be computed as a sum of Witten diagrams in ADS that we then integrate over the boundary. So now here's a fact that follows from supersymmetry. So if in the computation of correlation functions of operators that are invariant under the supersymmetry algebra on the sphere, so these are correlation functions on the sphere, the supersymmetry algebra is SU2/1 times SU2. So for example, one of those operators would just be the integral of ij plus k, so it would apply to the situation above. So if in the computation, of correlation functions of such operators using Witten diagrams, bulk vertices that are Q exact with respect to some supercharged Q that lies inside this SU2/1 algebra do not contribute. So this fact follows from supersymmetry, Q exact terms do not contribute to correlation functions of supersymmetric operators. So the question of what is the sphere of free energy computing in the bulk boils down to which bulk interactions are Q-exact and which ones are not with respect to a supercharge in this SU2/1 algebra. And this is just a question about, because we're asking it in ADS4, it's about correlation functions in superconformal field theory. There's a question about OSP24 representations and N = 2 effective field theory in ADS. So I want to describe to you the answer to this question. Okay, so one obvious way to answer this question would be to ask somebody who knows something about superspace. The point of the rest of the talk is even if you don't, there's still hope. So let me try to explain how to address this question. So first of all, it would be nice to have some list of interactions in ADS. I don't know where to find such a list, but what I know where to find is if we have superconformal field theory in flat space, in 4D flat space, then I know where to find a list of interactions that preserve N = 2 supersymmetry, and this is this paper by Cordova, Dumitrescu, and Intriligator. And the interactions are F terms, D terms, quarter BPS terms, and something they also call flavor current terms. For quantum field theory in ADS, the interactions, of course, have similar names. But the difference is that supersymmetry, in the expression that we write down, supersymmetry may require 1/L corrections. I don't know for a fact that these things here would be a complete list in ADS. Let's just study the analogs of these interactions in ADS and see which of them are Q-exact and which ones aren't. Okay. So what's a supersymmetric interaction? A supersymmetric interaction is some integral over ADS of some operator, and with the property that if we take the supersymmetry variation of that operator, we should get a total derivative such that the supersymmetry variation of the action vanishes. What's different between ADS and flat space is that the supersymmetry parameters, so this delta is epsilon times Q. Q is the supercharge acting on the operators, and epsilon is the parameter. In flat space, the parameters are constants, and ADS, the parameters are killing spinors, so they depend on position. So in particular, it won't be enough to say that Q acting on O is a total derivative because epsilon depends on position. We want this whole thing to be a total derivative. That's probably a technical term, technical issue. Okay, so what about the Qs? So what is the supersymmetry algebra, and how can we write down these interactions? So the N = 2 ADS supersymmetry algebra, as I said, OSP2/4, it has various generators. It has bosonic generators and then fermionic generators. The bosonic ones are like the momentum generators. These act like as covariant derivatives on the fields. There's Lorentz generators, local Lorentz generators, and U on R symmetry R. And in addition, there's 8 supercharges because 2 times 4 is 8. And there's 4 of them that have R charge +1 and 4 of them that have R charge -1. And I wrote them here with the corresponding indices that denote their R symmetry. And in 4 dimensions, spinors can either be left-handed or right-handed. So I'm going to denote the left-handed supercharges with lower indices and the right-handed supercharges with upper indices. This is sort of a common notation and in N = 2 supergravity theories. So then one can consider commutators between all these operators, commutators or anti-commutators. Many of them are as in flat space, as in the N = 2 algebra, the supersymmetry algebra in flat space, but some of them actually acquire corrections that are proportional to 1 the radius of ADS. So L is the radius of ADS, or 1/L². So for example, the commutator of 2 momentum generators is Lorentz generator, just because in ADS, unlike in flat space, covariant derivatives don't commute. Okay, so then with this notation, I can describe to you what possible interactions there are, and I'll tell you which ones are Q-exact. So the first one is the analog of a chiral F term. So in flat space. So suppose we have some operator A in ADS or field, it could be a composite field in ADS that's annihilated by all of the right-handed supercharges. Then what we can do is to act on it with all the left-handed supercharges, 2 of negative R charge and 2 of positive R charge. This by itself won't be supersymmetric. One has to add 1 over L corrections, but one can make this quantity here, and that's supersymmetric, and that's the ADS analog of a chiral F term. We can have another possibility where suppose we have some other field B that's annihilated by all the supercharges of R charge plus 1. So then what we can do is we can act on it with all the supercharges of R charge minus 1 to make this interaction operator. And this by itself, if we integrate it over ADS, will be supersymmetric. So the delta of this would be a total derivative. Another possibility is to have a D term. So suppose X is some field in ADS that's not annihilated by anything. So then we can act on it with all the supercharges. So I ordered them here. First, all the ones with R charge minus 1, and then all the ones with R charge plus 1. And then we can have quarter BPS terms where this some field C that's annihilated by only the supercharges of R charge plus 1 and left-handed, and then we can act with all the 6 other ones on it. And this is also supersymmetric. Of course, in all these cases, we can interchange plus and minus and also get a supersymmetric interaction. And there's also like a flavor current term, which has a more involved construction. So this here one starts with the triplet of scalar operators that obey a slightly more complicated shortening condition, and then acting on them with 2 supercharges, one can make something that's supersymmetric. It's called a flavor current term because if we act with some supercharges on these operators, the scalar operators J, we're going to get a conserved current. Okay, so these are the types of interactions that I'm going to talk about. As I said, it's just an exercise. Figuring out which of them are Q-exact is just an exercise in the supersymmetry algebra. So let me just tell you the result. I'm going to spare you the details. It's not an easy exercise in supersymmetry algebra. It's a complicated exercise in supersymmetry algebra. The result is that all the interaction terms that are written as all the supercharges with R charge minus 1 acting on something are Q-exact with respect to this SU2/1 supercharges. And it's the same if we replace plus with minus. So this is what we could prove. And so what does this mean? This means that, combining what I said before, that the sphere free energy, F of M, is independent of all the interactions that look like 4 supercharges of R charge minus 1 acting on something. So in particular, it's independent of both D terms, quarter BPS terms, and non-chiral F terms, because so these 3 in the middle, because they all look like all supercharges of negative R charge acting on something. This is the very large class of bulk interactions that the sphere free energy of the boundary theory does not depend on. And what does it depend on? Well, the other 2, namely, it could depend on chiral F terms. And just to give you a feeling for what these might be, pre-potential interactions are chiral F terms. And another thing that could depend on is these flavor current terms, and those correspond to mass terms for hypermultiplets in ADS. And so just this argument doesn't show that F does depend on chiral F terms and the flavor current terms, but we checked in explicit examples that F does depend on such interactions. So well, this could be the end of the talk. But I wanted to do a few tests because we learned a lot. We learned a lot from doing tests. So I just want to describe a little bit of that as much as I can. I probably won't get to everything that I have. Like some tests by constructing some explicit Lagrangians with interactions and seeing what the free energy, computing the sphere of free energy and seeing what it depends on and what it doesn't depend on. So one fact is that when we construct Lagrangians, we need to have some multiplets that we can work with, and ADS multiplets with spin smaller, at most equal to 2, are dual to single trace superconformal field theory multiplets. So it's good to keep in mind this correspondence. So with n equal 2 supersymmetry in ADS, various multiplets that one can consider is a big list: hypermultiplets, vector multiplets, gravitino multiplets, graviton multiplets. Many of them are complicated. I just want to, for some simple test, I just want to restrict to vector multiplets, massless or massive, and hypermultiplets. So what's a hypermultiplet? A hypermultiplet is a multiplet in ADS that has 4 scalars and 2 fermions. And if we give it a mass, let's say positive, then this would be dual to a chiral multiplet in the n equal 2 superconformal field theory on the boundary. And this is the correspondence. So that multiplet has a conformal primary of some dimension delta, then some fermionic operator of dimension delta plus a half, and then another complex scalar operator of dimension delta plus 1, and these would have their dual fields in the bulk. Another multiplet that one can use in ADS is a massless vector multiplet, which is dual to so massless vector multiplet in the bulk. This is dual to a conserved current multiplet in the boundaries theory. The conserved current multiplet in the 3D n equal 2 superconformal field theory, we've discussed that before. It contains the 2 real scalar operators J and K and the conserved current J mu. These operators in the boundary correspond to some fields in the bulk. And this operator is very important because we want to consider a real mass deformation on the boundary theory. So that's the deformation by this operator ij plus k integrated over the sphere. So it's this operator that this multiplet, massless vector multiplet, that we'll use in the bulk to describe that deformation. And then a slightly more complicated multiplet that you probably haven't seen very often is a massive vector multiplet in the bulk, which is dual to a long scalar multiplet in the boundary superconformal field theory. Starts with a real scalar of some dimension delta. There's the superconformal primary, and then it has some spinor operator of dimension delta plus a half, then 3 other scalars of dimension delta plus 1, as well as a spin 1 spin 1 operator that's not conserved in the boundary theory. This is what's dual to the massive vector in the bulk. And then some other spinor operators and some scalar operator of dimension delta plus 2. The mass of the vector is related to this delta. So these are the kinds of multiplets that I wanted to consider just for purposes of doing tests. So the first test would be something simple without any interactions. Suppose we take one of these multiplets that I described and we put them in ADS and we compute we do the Gaussian integral over these fields, and we extract the sphere free energy of the boundary theory. Suppose that we think about ADS with a sphere boundary. So for a bulk field, a free bulk field, whose dual has some operator of dimension delta and spin L, the contribution to the sphere free energy is given by some complicated expression. There's some term involving some zeta functions because this Gaussian, this one loop determinant is computed using zeta function regularization. And then there's some term that depends, that's actually divergent, depends on some UV cutoff. And, but it's also there. So what kind of test am I thinking about? Well, let's just take the last multiplet that I discussed, the free massive vector multiplet. And just add, for each operator in here, we know the dimension, we know the spin, we just add all the contributions. Then, it's complicated expressions, zeta functions, divergences, but surprise, almost everything cancels, and the answer is 5/24. And the point is that this is independent of delta. Is the same for any delta, or in particular dependent on the mass of the vector multiplet. And this suggests this changing the mass of the vector multiplet is Q exact. So changing the mass is not one of those special interactions that the sphere free energy depends on. By contrast, as I said, one of the interactions that one of the things that the sphere of energy depends on is the masses for a hypermultiplet. So if I do the same thing for a hypermultiplet, I do get something that does depend on the mass of the hypermultiplet. So this is what shows that that the sphere of energy does depend on flavor current terms. An example of which would be hypermultiplet mass. Okay. So the next thing I wanted to show you was a slightly more complicated test, which is a computation of an integrated 4-point function. So suppose we take 4 mass derivatives of f and we evaluate them m equals 0. This gives this operator integrated over the sphere. And I wanted to show you this in 2 models. One of them where this thing should depend on the bulk interaction, and one in which it shouldn't. So the one where it should is if we take a massless vector multiplet in the bulk and we give it a self-interaction with a quartic prepotential. So this is the prepotential interaction. And another one would be if we have, of course, this massless vector multiplet and consider the exchange of a massive vector multiplet. This is not one of those interactions. So the free energy should not depend on these vertices that we have here. But of course, there's a problem when you want to do a test like this. The problem is that you actually have to write down action in the bulk that's supersymmetric. The question is, what are the supersymmetry preserving interaction vertices? And also one has to also calculate the corresponding Witten diagrams and integrate them over the boundary. And the second point is easier than the first. Matt, how much time do I have? Is it like another?
Yeah, I mean, so technically it's 45 minutes total. So I mean, yeah, if you can try to wrap up in the next few minutes, I don't know if you're close to that. Can you try to wrap up in 5 minutes?
I can try to give a summary.
Yeah.
Of this. Right. So, okay. So the first thing that I wanted to say was that, well, you couldn't just look up a paper to read off the supersymmetric interactions in ADS. So we just had to find, especially for the massive vector multiplets in ADS, we just had to find a way to extract them by taking some limit of some supergravity theory, n equal 2 supergravity theory coupled to matter, the limit of where the Newton constant goes to 0. This way we constructed some gauge theory with massless or massive hypers in ADS, and well, there's various Lagrangians that one can write down. Write down Lagrangian for a massless vector multiplet with no interactions. It's just quadratic Lagrangian. Then one can give it a quartic prepotential interaction, and then there's some interaction terms that are written over here. One can simplify it, and the interaction terms would just look like that. this is just the expression for the scalar in this vector multiplet. Then one can try massive vector multiplets. Yeah, and this is something I want to explain very, very briefly, because if you look through the literature, you're not going to find an action for a massive vector multiplet. So the way to construct it is this: without supersymmetry, a massive vector is a massless vector plus, using the Stuckelberg trick, plus a scalar with the gauged shift symmetry. So one can write down the Maxwell Lagrangian, and then a Lagrangian for a scalar field with a gauge shift symmetry. So the kinetic term would be d mu phi minus a mu with some constant here, mv. And then if we redefine b mu as a mu minus 1 over mv times d mu phi, and g mu nu is the field strength of this new vector field b mu, then the Lagrangian is just the same as the Prokop Lagrangian for a massive vector multiplet. Okay, so this is without supersymmetry. With supersymmetry, it's the same thing. Take a massive vector multiplet is constructed from a massless vector multiplet plus a hypermultiplet, where one of the 4 scalars of the hypermultiplet has a shift symmetry that's gauged. So, using our formalism, we can write down a Lagrangian for that. It's like some scalar fields from the vector multiplet, some scalar fields from the hypermultiplet. There's 3 of them that don't have a gauge shift symmetry, and 1 of them that does, and one redefines the fields, and one finds this quadratic action, and the masses of all the fields match are consistent with the operator content of long scalar multiplet in the boundary theory. And then, of course, one can consider a combination of a massless and a massive vector multiplet interacting, and using this formalism, one can write down the interaction Lagrangian. Here I wrote down all the vertices that are relevant for these type of diagrams. Okay, so that's one thing, and then the other that was writing down the actions. And now to compute this quantity, one needs to integrate Witten diagrams over the boundary points. So for example, if one starts with some exchange Witten diagram, boundary operators of dimension delta 1, delta 2, delta 3, delta 4, exchanging a bulk field that's dual to some operator of dimension delta, that's the exchange diagram. And then one would have to integrate it over the boundary points. It's not as bad. There's many integrals here. There's like 4 plus 4 plus 3 times 4. So 12 plus 8, 20 integrals. But one can actually do them using the split representation of the bulk propagator, and one can find the answer that there's some answer that depends on the dimension of the operator dual to the field that's being exchanged. The answer is quite complicated. It just depends on this third derivative of the logarithm of the gamma function. So this is the integrated exchange diagram. Integrated contact diagrams are easier to calculate, but let me not explain that in detail. So now this would be the punchline. The punchline would be that if we could put everything together, interactions and these integrated diagrams in 2 models. So the first one would be a massless vector multiplet with this prepotential quartic interaction. And indeed, if we compute the 4th derivative, it's proportional to this coefficient beta of the prepotential interaction. And then in the other example, we have a massive vector multiplet and a massless vector multiplet interacting. If we add together all the exchange diagrams, we exchange the fields in the massive vector multiplet and all the contact diagrams that are required to be there by supersymmetry, the whole thing gives 0. So the sphere free energy of the boundary conformal field theory does not know about scaling dimensions of unprotected operators or about the interactions of the massive fields in the bulk with the massless ones. So the other 3 slides that I had before the conclusion slide were about some work in progress that I can mention only very briefly. That as I mentioned before, people noticed that for ABGM theory and another model, the sphere free energy of the boundary theory is proportional to the pre-potential in the bulk. And so it's a couple of examples. So what I've been doing with Dan and Bernardo is to explain this a little in more detail and have a conjecture for how exactly to extract the sphere free energy from the pre-potential. So suppose I just give you some effective theory in the bulk with some pre-potential, suppose some vector multiplets, some pre-potential, and then maybe some hypermultiplets, and we actually have a prescription for figuring out exactly what the sphere free energy is in terms of the pre-potential. So that's just work to appear. So conclusion: S3 free energy in theories with holographic n=2 theories with holographic duals receive contributions only from a very special set of bulk interactions. In particular, sphere free energy does depend on the pre-potential interactions, but not contain information about massive vector multiplets. And then questions for the future. Well, prove this conjecture that we're going to make about relating the sphere free energy and the pre-potential of the supergravity theory, and other dimensions. It's something that I find, I don't know much about this last point, but I find intriguing the fact that the sphere free energy deformed by the masses in the boundary theory does not seem to capture a set of protected data that I can easily explain what it is. But in the bulk, the situation for a theory with a holographic dual, the situation is much better. It just captures a very, very protected set of bulk interactions. So that begs the question, is there a replacement for the usual superconformal block expansion that we do and in superconformal field theories that would also make obvious the data that is captured by the sphere free energy in a theory that may or may not have a holographic dual. So sorry, so that's all I wanted to say. Yeah, thank you very much.
Okay, thank you very much, Silviu, for the nice talk. Okay, so are there any questions? Yeah, so I see we have Yifan. Yeah, please.
Hi, Silviu, thanks for a nice talk. I think unfortunately I missed most of it, so this may be something you already covered. So could you say a little more about the boundary terms that are necessary to, in ADS4 to make sure the supersymmetry is preserved?
Oh, you did not miss that because I did not discuss any boundary terms that might be needed in ADS4.
That's important, right? For when you want to kind of do a precision matching between the bulk and boundary computation, you want to make sure both sides preserve the supersymmetry.
Yeah, of course.
Yeah.
That's important. Yeah. So I discussed, if you missed that, some bulk interactions, and the only condition that I imposed to ensure that the bulk interactions are supersymmetric is that, so the bulk interaction is some integral of some operator, and I impose a condition that supersymmetry variation of that operator is a total derivative. But I did not, so I would then assume that with appropriate boundary terms, one can make it a supersymmetric interaction, but I did not, I did not do that. And they did not come up for any of the computations that we did, those boundary terms.
That's surprising because you had this nice paper with Dan and the collaborators where you showed that, for example, for the three-point function of the PPS operator, the boundary term is crucial to reproduce the boundary result.
Yeah, so, okay. So in this talk, I avoided those three-point functions. I only talked about four-point functions.
I see.
That's right.
But the information about the three-point function is somehow contained when you factorize the four-point function.
Yeah. So that if one is careful about supersymmetric regularization, that would have to be included. Mm-hmm. If one is careful about preserving supersymmetry, yeah.
Okay. Anything else? So if not, I mean, we're a little bit behind schedule. So I think, Silviu, are you going to be here for the discussion session or?
Yeah, I'll be there.
Okay, so maybe we'll postpone more questions to there and take a small break and meet. I think Yifan is actually going to be giving the next talk. So maybe let's thank Silviu again. Thank you. And let's maybe end the recording.